Good morning, everyone. My name is Edoardo Ricca. I am a research fellow at the University of Trento, and today, with my colleague Davide Vignotto, we will present you the latest developments in the analysis of the grabbing, positioning, or release mechanism from the LISA Pathfinder mission. First of all, let's start with a quick recap of the mechanism. Its main tasks are to release the test mass into free fall and to handle it just after the launch phase, or in any case, the safe mode activation is required. As you can see from the rendering on the right, the mechanism is composed of two halves. Each half includes a plunger with its coaxial golden tip. Both the plunger and the tips have dedicated mechanical interfaces on the test mass that are respectively called test mass indents and landing area. It is important to study this mechanism because 6 of them will be implemented in the forthcoming LISA mission. The test mass release procedure consists of 3 sequential steps. The first one is the grabbing. In these steps, the plungers moves towards the test mass, inserting their heads into the test mass index. The second step is the handover. Here there is the transition from the plunger to the tips. At the conclusion of this step, the tips touches the landing areas of the test mass. The last step is the actual release of the test mass, which is performed by a quick and simultaneous tip retraction. Given the symmetry of the system symmetry and according to the procedure, the test mass release velocity should be directed almost totally along the z direction. After the release, the test mass is controlled and stabilized by the electrostatic actuation force. As you can see from the picture on the bottom, an additional thing to note is that the clearance between the plunger and the test mass is small with respect to the extension of the mechanical interfaces. In this slide on the right, you can see the telemetry signals of the first in-flight releases performed in February 2016. In the table, the velocity data that can be extracted from those signals are presented. As you can see, the velocity, the test mass residual velocity, were higher than the requirements that are of 5 micrometers per second for the linear velocity and 100 micrometers per second from the angular ones, and were even different from the expected ones. As a consequence, at the end of the mission, an additional experimental campaign was carried out, testing different release strategies. Some mitigation maneuvers were implemented, even if no optimal release strategy was found because the two mechanisms behave differently under the same testing condition. This type of unexpected velocity, of unexpected dynamics, could be explained by contact between test mass and plungers. But how it is possible that the impacts between plunger and test mass took place? There are several factors that can reduce the nominal gap between test mass and plunger. Those factors can be divided into statics one and dynamics one. The static factors are the ones that reduce the clearance just before the release, the test mass release, when the bodies are still. Between those, we have the alignment uncertainty during assembly and integration of the mechanism, and credits for this one goes to OHB Italia. Then we have the plunger B-stable behavior, as you can see on the picture on the right. Then the large uncertainty on the tip stroke. The nominal one should be 18 micron, while on-ground test shows that we are closer to 15 micron. The machining tolerances can, of course, affect the geometry of the mechanical interfaces. And the last one, in some cases, there is the preload force on the test mass that is not sufficient to constrain it properly. The dynamics factor are the plunger oscillation triggered by the fax tip retraction. In this presentation, we will analyze the hypothesis of oscillating plunger impacting the test mass. The problem of extracting meaningful information from the in-flight data is that the GRS is not designed for this type of analysis. In fact, the sampling frequency of the telemetry is too low. It's just 10 Hz, while the natural frequency of the plunger are greater than 1 kHz. For this reason, some tests resulted not reliable in terms of the estimated test mass residual velocity. Regarding the one instead that resulted reliable and non-compliant with the requirements, the release dynamics was planar for almost any of them. In fact, as you can see from the picture on the bottom part of the slide, the impulses received by the test mass lie on the XZ plane. From now on, the presentation will be headed by my colleague Davide Vignotto that will discuss about the on-ground testing and the following analysis.
Good morning, everyone. My name is Davide Vignotto. I'm a PhD student at the University of Trento. I will continue the presentation describing the experimental setup that was used to characterize the plunger motion. We have a vacuum chamber mounted on top of an anti-vibration platform, and inside this chamber there is one half of a GPRM. With a laser interferometer pointing the plunger in two directions, we can characterize its motion on the plane. The laser can be pointed laterally, so along X direction, in the reference frame that we can see in the central figure, or axially, so along Z direction. When pointing along Z direction, we are in fact measuring the tip motion and not the plunger motion, because there is no frontal flat surface on the plunger. On the graphs on the right, we can see the displacement recorded with this type of experimental setup along the axial and one of the several lateral positions in which the laser was pointed. In order to develop a test mass plunger collision model, the motion of the plunger needs to be known. For this reason, it is necessary to build a model which, from the tip motion, describe what is the plunger motion. In order to do this, an electromechanical lumped parameter model was built and to estimate the plunger axial oscillation. So the model starts from the scheme that you can see in the figure on the left, and the model itself is schematized in the central figure. We can see that also the circuit needed for the actuation of the piezo-stack moving the tip is modeled. And while on the graph on the right, we can see the result of the fitting of this model to the measurements. We can see that the blue curve, so the tip motion measured with the laser interferometer, is fitted by the orange curve, which is the tip motion predicted by this model, while the green curve is the plunger motion. And we can see that it is very different from the tip motion. So, given the model estimated axial displacement and the measured lateral displacement of the plunger, the trajectory of its center of mass in the plane has been computed under the rigid body assumption. From the CAD model of the mechanism, the expected test mass plunger contact point was found, and its trajectory is plotted in the graph on the right. In the plot, also two directions are highlighted. One is parallel to the indent of the test mass, and the other is orthogonal. The estimation of the contact point is affected by a small uncertainty if compared to the dimensions of the body here considered. After characterizing the contact point trajectory, the test mass plunger collision was modeled under some assumption. So the strains are much smaller than the body dimension. The impact forces are much greater than all the other forces. The collision is instantaneous. We have a negligible friction, so the impulse is orthogonal to the colliding surfaces. And we have a unitary coefficient of restitution. Moreover, the model considered just one single impact between the test mass and the plunger. So the inputs of the model are, of course, the velocities of the body before the collision, and the output are the velocities after the collision. In this graph, we have a schematic visualization of what we expect from the application of the model. So we have the top graph representing the plunger displacement towards the test mass in the direction orthogonal to the indent. And we see that this graph defines some time interval in which the collision may occur. Those intervals correspond to the one when the plunger is moving towards the test mass. In those intervals, the kinetic energy, which is plotted in the bottom graph, is limited to some values, and some of these values are equal to the kinetic energy that was measured in flight, which is the red line we see on the bottom graph. In this particular case, schematized, we have 3 points, 3 blue dots, that corresponds to points, to time instants, where the kinetic energy measured in flight is equal to the one predicted by the model. Now, the application of the model to the in-flight data of one of the tests performed is shown in the two graphs on this slide. We see the distance covered by the plunger towards the test mass on the top graph, and the kinetic energy on the bottom graph. In this particular case, which resembles the schematic one seen before, we have 4 possible instances of collision where the kinetic energy measured in flight equals the one predicted by the model. And the main difference between these two graphs and the ones presented before is the presence of bands around the mean curve. Those bands represent the propagation of the uncertainty. Some observation, we see that the estimated kinetic energy is compatible with the in-flight release for all reliable non-compliant tests. And then we see that the test mass plunger gap is between 0 and 0.5 micron. So in other words, the test mass is very close to the plunger at the release. Of course, this model has some limitation. First of all, it describes what happens in case of a single impact. And then it's not able to describe what happens in case there is a static push of one plunger on the test mass. So here we come to the conclusions. We have seen that the reliable non-compliant test performed in flight can be interpreted with the test mass plunger collision model, and which explains that the oscillation of the plunger may be the cause of the kinetic energy of the test mass that we have seen in flight. The collision is possible if we consider that there are many static factors that can reduce the nominal clearance between the test mass and the plunger before the release. It is very important to optimize the GPRM because 6 GPRM-like mechanisms will be integrated in the 3 spacecraft of LISA mission. So what we highly suggest is the introduction of a test mass plunger gap budget during the MAVE of the mechanism. Thank you for your attention.